Advanced Math Lesson 53, Review of Unit Multipliers and Angular Velocity. Okay, we're just going to go straight to angular velocity, and I should also call this linear velocity, but I guess it's mostly based on angular velocity. So again, angular velocity, they're referring to an object like, if you imagine a bug getting squished by a tire, the amount of times the bug goes around the tire would be considered an angular velocity. However, if you were to think about the very center of the tire, the center of the tire doesn't actually move. The center of the tire moving across the surface, or how fast the axle that the tire is mounted on is traveling, or the actual velocity of the car, would be considered linear velocity, because it's a straight line movement, whereas the bug on the wheel is just going in circles over and over and over and over and over again, and that would be an angular velocity. This is a pretty good drawing that they use to express it. This dot being the bug on the wheel, and figuring out its vector velocity going in that circle, whereas if we were looking at the axle, it would just be going in a straight line across the surface of the floor. So linear velocity, angular velocity. Now there's one equation that we need to memorize in respect to these problems, and it is this. And this is for linear velocity. So linear velocity is equal to radius times omega. That's a terrible omega. It's kind of like a funny italicized W. And omega is actually the representation of angular velocity. So this weird omega symbol is equal to angular velocity. And V is just equal to linear velocity. So let's look at an example of a problem we've got here. They tell us that a wheel of a wagon has a radius of 14 inches and is revolving at 40 revolutions per minute. How fast is the wagon moving in miles per hour? So let's go ahead and write this information down. We have a wagon wheel with radius is equal to 14 inches, and it's traveling, and the wheel is rotating at 40 revolutions per minute, and this is an angular velocity. Now it's not our specific omega velocity that we're looking for, because omega velocity is typically represented in radian measure, which is why we learn radian measure. So the first thing we need to do to start solving this linear velocity problem, because they want to find how fast the wagon is moving, which is a linear velocity problem, we have to take our omega, or our angular velocity, and convert it to radians. How do we convert it to radians? Well, this is the exact same conversion rate, which is that one revolution would be like one time around. So that would be like one circle. So the conversion rate we're going to use is 2 pi radians over revolutions. So that's one of the conversion rates that we would use. You can also use degrees for these problems as well. If we had to convert for degrees, say it was 40 degrees a minute. Wow, that's a really slow rotation. 40 degrees a minute would be 2 pi radians over 360 degrees. Because, again, unit multipliers are supposed to be equal to 1. So 2 pi radians would be 360 degrees over 360 degrees. That would help us cancel the degrees and convert us to radians. Now here, 1 revolution is equal to 2 pi radians. So we cancel the revolutions, and what we end up getting is 40 times 2 pi, going to give us 80 pi radians over minutes. And that is going to be our angular velocity, or our omega. I'll get better at writing those W's eventually. It's just an italicized W. No, that one's ugly. Hold on. There we go. That's a little better-ish. Okay, so that's our omega for this problem. And again, remember we said velocity is equal to radians, or not radians, radius times omega. So if we want to find the velocity of this wagon wheel, we have to take our radius of 14, multiply it by our angular velocity of 80 pi radians a minute. So velocity is going to equal 14 times 80 pi Whoops, that's 80 pi radians a minute, and I forgot this is 14 inches. So when we finish multiplying all of that, what we end up getting is, or to simplify it, we get 14 times 80 pi inches and radians over minutes. Now, this is our actual velocity of our wagon, but the problem is they want us to put our answer in miles per hour. And this is where unit multipliers comes in. So we're going to take our good answer and we're going to use unit multipliers to convert the inches to miles and the minutes to hours. I'll go ahead and start with minutes to hours. So if minutes is on the bottom, I'll put it on the top. And there are 60 minutes in 1 hour. So their minutes cancel and I'm left with hours. So that one's done. Now let's go from inches to miles. And I'll just tack on this unit multiplier right next to it. Inches is on top, so I'm going to have to put it on the bottom. There's 12 inches in 1 foot. Inches are now canceled. And then I have to go from feet to miles. So feet is on top, I put it on the bottom. There's 5,280 feet in 1 mile. Whoops, that says minute, mile. Feet cancel. And then from here, I'm just going to simplify all of this by writing it out in one line. Anything that didn't get canceled is going to be my answer. So I have 14 times 80 pi, or 80 pi radians, times 60, and 1, okay, so that's it for the numerator. The denominator, I have 12 and 5,280, so 12 times 5,280, and the only words I have left are, let's see here, radians, and then miles, and then hours. So this is going to be miles per hour. Again, I'm not going to write, well, not again, but I'm not going to write the word radians because that's already signified by 80 pi. So this is my final answer. And no, you do not have to multiply this out in your calculator. This is what the book is looking for. So we solve it like a unit multiplier problem, where we keep all of our units separated. The only thing we're ever going to actually multiply is if we have to multiply 2 units to find our omega. So this is the final answer. This is how fast the wagon is moving in miles per hour. Now, let's say we have to find an angular velocity. So that was a linear velocity problem. Let's find an angular velocity problem. They tell us an automobile whose wheels are 30 inches in diameter is traveling at 40 miles per hour. What is the angular velocity of the wheels in revolutions per second? So here we've got something at 40 miles per hour, and we have to convert that to revolutions per second. So let's go back to writing down our information. They say if the diameter of the wheels is 30 inches, we have to know the radius. So the radius would be 15 inches, which is just the diameter divided by 2. So I don't care about the diameter. I do care about the radius, because the equation I'm using again is the linear velocity is equal to the radius times omega. In this case, our linear velocity is 40 miles an hour. So if I were to substitute, so if I were to substitute in here, that's miles over hours. I could plug this in. It would be 40 miles over hours equals 15 inches times omega. So to solve for omega, I would divide each side by 15 inches. That cancels. So then I get that my omega is equal to 40 miles an hour over 15 inches. I'm going to go ahead and simplify this problem using complex fractions. So if I write it down like this, I can simplify it by inverting and multiplying. So I have 1 over 15 inches. And what this turns into is it just equals, I'm going to write it on this side, 40 miles times 1 is just 40 miles, and then 15 inches times hours is 15 inch dash hours. And that's how you write units when they get mashed up together like that. You just put a dash in between them. So that is our angular velocity, right? The problem is our angular velocity is typically in degrees, radians, or revolutions. And our answer, they want it to be in revolutions per second. Now, in order to get to revolutions, I'm going to convert this to radians, and then I will convert the radians into revolutions. So I'll go ahead and use some unit multipliers, and we'll start converting this. So let's get rid of, oh, that's one thing. We've got miles and inches, right? So I actually have to get rid of inches and cancel them. So I can either go from inches to miles or miles to inches. But I need to cancel both of these distances so I can get them into revolutions per second. And this will work out depending on which one you choose to cancel. I'm just going to go ahead and cancel inches to miles. So if I put inches into feet, there are 12 inches in 1 foot. So inches have gone ahead and canceled. And then if I keep multiplying and I go from feet to miles, there are 5,280 feet in 1 mile. So here miles cancels, and feet also cancel here. So by doing that, I've eliminated the inch and the mile rate. And now I need to convert hours into seconds because they want to do revolutions per second. So for hours, I'm going to put that on top since it's on the bottom. So hours on top. And there's 1 hour and 60 minutes. So hours is canceled, and then I have to cancel minutes into seconds. So there's 1 minute in 60 seconds. So minutes is canceled. So I've done a lot of unit multipliers. I'm going to go ahead and rewrite these to simplify it. So right now what I've got on the numerator is 40 times 12 times 5,280 times 1 and 1. Those don't get written down. The denominator, I have 15 times 60 times 60. And this answer is actually in radians per second. In this case, I'm writing radians because there's no pi value. And again, I know it's in radians per second because I just solved for omega, which we said before, omega is always in terms of radians. So once I solve for omega, this is the value in radians per second. And it's okay that pi doesn't show up here. Now the last thing I need to do is convert the radians to revolutions. So we'll go ahead and multiply this by our unit multiplier of, if radians is on top, it goes to the bottom. So 2 pi radians in 1 revolution, or 360 degrees. Radians cancels. And then I now have 40 times 12 times 5,280 over 15 times 60 times 60 times 2 pi from here. And that is now in revolutions per second, which is exactly what the problem wanted. So keep track of this equation, velocity equals radians times omega. Remember, omega is always in terms of radians. And then to convert your radians, just remember 1 pi is equal to 180 degrees, 1 revolution is 360 degrees. And it's just using a lot of unit multipliers. Make sure you don't forget any of your units, and then you take what you have and convert it to what you want. If you have any questions, let me know on Moodle, and I will see you in class.